New chapter today. Yeah. Chapter 6, Prandtl. Okay. Okay. It's all about friction. So we talked about dissipation, drag, and then there is friction, right? Friction is an old subject. So old that, look at this. This is a drawing by Leonardo da Vinci. Okay. Which question do you think Leonardo is asking here? What is his inquiry here? So he has a box. He puts it the same box. He puts it this way, drags it. He puts it this way, like. Okay, let me show it. I'm drawing something like this, but there's a better drawing by the best painter ever, right? He puts it this way, pulls it this way, pulls it this way, pulls it. So the question here is, how come friction doesn't depend on the apparent contact area? It doesn't make sense, right? You would expect when you have a block with larger area contacting the bottom, have larger friction, right? But that is not the case usually. Like in sliding friction, like take this one, drag it like this, and drag it like this, it will have more or less the same friction. Okay, puzzling. So that puzzle was solved. So let me just finish my ugly drawing. This puzzle was solved by Bowden and Tabor in 1940s. What is the answer? The answer is this. Whether you are putting it this way or that way, you think that the contact area is this, but that's only the apparent contact area. So let me write it down. Apparent contact area. Okay? But the actual contact area lies in microscopics, right? There are these protrusions here, microscopic stuff going into each other, and the contact area is where they touch each other, the sum of that contact area, right? So that contact area, real contact area is proportional to normal force. So the more you push it, the larger contact area you get, which is proportional to force of friction. That's why you have this mu times Fn in high school books. Are you happy? Yes? So one puzzle solved. Then there are other puzzles like this one. So we have seen Stokes' law, right? Stokes' law. Stokes' law tells you that friction, or let me call it drag, is proportional to velocity, right? Do you remember gamma v, drag? Very good. But then there is Coulomb's law. Same Coulomb, different law. Okay? It's not k q1 q2 over r squared. This one, it's this friction, but this is sliding friction, okay? Sliding friction is independent of velocity. okay? Because if you take this one, 0 velocity, push it, I'm pushing it, but it's not moving because there is this static friction. But even once it starts moving, I'm still pushing it with very little velocity, let's say, and it's nowhere near gamma v. It actually starts at some value. Maybe it depends on velocity a little bit. Maybe the more you push it, the more drag you get. But sliding friction is really, main portion of it is independent of velocity. So what is going on? Two laws that seem to be against each other, right? And we resolve it with so-called Prandtl Tomlinson model. It's mainly due to Prandtl, really, okay? So you can call it Prandtl model as well. So here's what Prandtl model considers. Again, sliding friction, but let's take the bottom part as a sinusoidal potential. And at the top, there is a protrusion. Okay, we will focus on one protrusion, let's say something stiff. It has some stiffness, okay? It has some stiffness, this part. And this part has some corrugation. In Prandtl Tomlinson model, it's all about stiffness versus corrugation. I will explain it, okay? I will explain it. So let me draw it without any material. So basically you have a potential, and it's a sinusoidal potential. Okay. And you have, let's say you have you have the tip of the tip. So you have a tip like this, which is stiff, and its tip is staying here. It's very hard to justify it. You have a ball, okay? It's just a ball sitting there. Where would this ball go? It would go to the bottom of the potential. Do you agree with that? But that's not the end of the model. There is another thing here. There is a spring here. We are pulling the spring with velocity v spring, and this is the K of the spring. So what do you expect? Let me give you the formula first, the whole model. Okay, you have the position of this ball, d squared x over dt squared, F equals to ma, right? This is ma part, equals to, what do we have? We have del v x over del x with a minus sign. What is this? This is the force, right? Negative derivative of potential is force. Do you agree with that? This is external force. Then we have plus K spring. Should I go with K spring times V spring times time minus X. Okay? So it's pulling with constant, it's going, the spring is moving with constant velocity, and it wants to drag the ball with it, right? But the potential wants to put it inside its minimum, so it will just bump from one to the other. So it will be like tick, 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 like that, okay? But it will not always be like tick. Okay, we will see it. Then we can add our usual suspects, which is, okay, where should I add it? Let me add it here. I have the dissipation. This is microscopic friction. This is the friction that we have already analyzed. But there will be more. On top of that friction, we will have more friction because of this ticks. Okay, I will see it. Plus this thing that we discovered last time, 2 gamma kBt, so fluctuation and dissipation. Let me write it like this, and multiplied by a Gaussian. Okay, so what do we have? Let's go over the terms. This is inertia, this is corrugation, this is the spring, this is dissipation, and this one is fluctuation. I mean, we can take, okay. Let me give you an extreme case. Extreme situation number 1. Number 1. Very stiff spring, very smooth potential. What do we have here? Basically, if you draw the potential of the spring, it looks like this, okay? While the potential of the corrugation looks like this. Okay? The potential is very weak. So what will happen? It will not do this tick, tick, tick. It will just do this. So it's so stiff that it's like a pencil moving over a potential that is not really corrugated. It's like this. So it will be like this. Yes? Okay? Are you following? Yes? So this is what we call super lubric regime. Sure, of course. So as I said, it's all about stiffness versus corrugation. Okay? If this protrusion is super stiff, it's like made out of metal or something, okay? And the thing underneath is very smooth. It's like cotton or something, right? It will the strong spring, the strong corrugation will not get stuck. It will just go over it without even caring what's happening. So that's the super lubric regime. Does it make sense? So in the super lubric regime, really the only friction that you get is due to dissipation. So indeed, you are in this Stokes regime. Friction is proportional to minus gamma V. Coulomb law doesn't apply here. Okay? Super lubric regime. Okay. Extreme situation case number 2. Very soft spring, very high corrugation. Okay, this time your spring potential looks like this. It's very soft. Okay, while the corrugation is like this. Okay, so the ball would like to stay here, while you are dragging it with a spring that has very low spring constant. So it will just clink there, and you are dragging until, of course, no matter how soft it is, at some point you will reach enough distance, right, so that it will just have to bounce out, right? But when it bounces out, all hell will break loose, right? Because now it has gathered all that potential energy and it's suddenly released. Sometimes it would just do one tick like this. Sometimes it will do double slip, like tick tick. Sometimes it will be triple slip, whatever. But during that slip, it will move very suddenly, very high velocity. I mean, its velocity over here, v ball, will be during the slip, or let me call it v slip, because v slip will be much higher than v spring. Because notice that our velocity here that goes into the equation, macroscopic equation, is the velocity of the spring. That's the system that is moving against the other system. But inside, microscopically, these things that are doing tick, 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 tick are moving way faster. Does it make sense? So since they are moving way faster, and since the microscopic friction is still minus gamma v, it will be minus gamma v slip. So it will be, first of all, much larger than minus gamma, much larger in magnitude. Much larger than this. And as you take v spring to 0, this will not be affected because it has nothing to do with that one. V spring, nothing to do, something to do with it. But no matter how slowly you approach this, once it's enough for this part, it will just move really fast. What do we call this regime? We call this regime stick-slip regime. Okay? And most of the things are in this regime. Most of the sliding friction systems are in this regime because being in superlubric regime requires having very, very smooth surfaces. Okay? And you usually don't have that. Okay. So how can we quantize? We can say that this potential is K spring x squared over 2, right? How can we quantize corrugation? We can quantize corrugation by saying that this thing over here is approximately minus K corrugation x squared over 2. So that's a parabola, this is a parabola. Does it make sense? You don't agree because it's a sine? No?
I just get tired of this.
Okay, no, but it works, right? It works everywhere. So if K spring over K corrugation is larger than 1, then you are in what regime? Superlubric regime, very good. Then you are in superlubric regime. Should I call it like this so that it's clearly over there? Spring over K corrugation is much less than 1, then you are in stick-slip regime. Okay. Here you obey whose law? Stokes' law. Here you obey Coulomb's law. So, paradox resolved, hopefully. But of course, we have code. This chapter is really boutique chapter. I think hopefully we will be done by it today, even with some spare time left. There's only one code. And let me go over it. Okay. Well, let me just run it, and then I will explain the code. Okay, it's running. We are really happy. So this is the corrugation. This is the ball. This is the spring, but it's represented with a stick. So this is where the spring is. It's jiggling around. Why it's jiggling around? Previous chapter. Like fluctuation, dissipation. Okay, it's fluctuating. It can't go down here. Why it can't go down here? Because apparently the spring is stiff right now. Let me soften the spring. Boom, it falls down. Let me stiffen it again, it goes up. Do you understand it? What is this one? This one is the potential of the spring plus the potential of the corrugation. So as I soften the spring, you can see that it makes a symmetry breaking phase transition, right? Like there is one point which is stable. Then as you increase the corrugation, it becomes that one stable fixed point. There's an expression there, fixed point. Okay, we will come to this. We'll talk about this a lot. Fixed points is where force is zero, let's say, right? But if you actually want to stay there, then it's a stable fixed point. If you want to go away from it, it's an unstable fixed point. So it's a stable fixed point. The ball wants to go there, and it stays there. Just jiggling just comes from dissipation, fluctuation dissipation. But otherwise, as you increase the corrugation, that one stable fixed point becomes unstable while creating two stable fixed points, right? Let's see it again. And where it will fall just is anyone's guess. It's symmetry breaking, right? Now let's start moving it. So, what do you think is this regime? This regime. What is this regime? Stick slip, right? Because corrugation wins. What is this regime? Super lubric regime. Now, let's start moving. So I start moving, and I get this force. What is this? This is force versus x, okay? Let me reset it and start moving to the left. Force. Force, okay? So, which double peak?
In the peaks, they are looking like a double.
It's fluctuating. Should I just set the temperature to 0 so that it doesn't fluctuate? It doesn't fluctuate now. So, well, do you see? Now let me go back. Okay, it does jiggle, sorry. So you see it's more or less the same kind of a force versus x, right? So how much friction do we have? We can see it from the area between these curves. But it's better understood when it's, let me just reset. It's better understood when it's in the stick slip regime. So let me switch to that regime, just stick slip regime. Look, it is stuck right now and the force goes up, and then when it's released, it goes down. Okay, let me go backwards now. Stuck, released, stuck, released, stick slip, okay? And the area in between is the energy that we lost. Because what we are doing, we are moving something, and we are looking at force, okay? If there is no friction, then let me think. When I move, so I pull it with force F this way, and then I pull it back that way. If there's no friction, the area underneath should cancel each other, right? But it is not. So the amount of that area, it gives you the friction, okay? You can also
Friction always opposes the motion, so I think it should be symmetrical. In both directions, actually.
I'm sure that this is correct, but let me say it another way, okay? You are pulling it, and you are basically looking at how much force it reacts to you're pulling. And you can see that while you are pulling this way, you are pulling on the average with this much force, okay? And this means that much force is opposing to you. When you are pulling that way, that much force is opposing to you in the reverse direction. If you don't believe this, let me show you experiments. So this is a famous experiment of microscopic friction. Atomic scale friction of a tungsten tip on a graphite surface. Very famous. So what they do is, if they press hard enough, you see the load is increased here, they actually do see this effect on an atomic level. So there's a tungsten tip going over graphite, and every time it passes through an atom, tick, okay, every time. So even if you are atomically flat, you can't get away from this stick slip regime if you have enough load. Of course, here the load is huge, probably. I don't know what do you get when you have it in pascals. It's probably gigapascals range of stuff, okay? But you can see that if you don't put that much pressure, you see this is 10 times less, right? So then you are in super lubric regime, sort of, because the corrugation is much smoother, right? So you can see that there are these smaller jumps, and then there are larger jumps, and those larger jumps correspond to double slips. So every now and then the tip just does tick tick. Okay, when it does that, drops even further. Okay, here it is. Doesn't work, I guess. Let me run it again. So if you are in super lubric regime, you don't really have that much area. Can I get rid of this too much thing if I increase this one? I don't want to. Maybe if I do this. Okay. I decrease the time step. It didn't matter, right? But at least we have a smoother curve. Okay. What is also no? Mm-hmm. So let me go backwards. You can see that when you go backwards, it's more or less going over the same path. Okay, I realize how I can make it smoother. I can go with less velocity. It will be boring. Where am I changing velocity? So let me do it this way. You see, it's not fluctuating that much anymore. As I promised, it's boring, right? Very good. You are convinced? Now let's go backwards. You will see that the difference is tiny. That area in between is the friction. And did you notice that when velocity was higher, that area was larger? So it is indeed proportional to gamma V in the superlubric regime. Yes? Good. So let's move to stick slip regime. And you are pulling, you have to be patient. Do you see how it gets stuck in the total potential and then just slips? Right? So you are pulling, and then moves suddenly. While it moves suddenly, you get that. That's where you lose energy. And as you can see, it's sort of independent of velocity. Okay? Any questions, comments, ideas? Yes?
In the previous one, I mean the velocity scenario, the slip stick regime was bouncing twice as much as.
Okay, yes.
But,
Yes, very good. So as you increase the velocity, as you change all those parameters, every now and then you enter these different regimes. Okay? Let me show you my PhD thesis. Blah 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 blah. Yeah. So this is the velocity, this is the average friction force. All these are different parameter regimes. Sometimes you enter a double slip regime. As you noticed, when you change the velocity, you can go from single slip to double slip, or you can go from single slip to triple slip, depending on what is your velocity. There are a couple of parameters here, right? You can play with them. Should you choose to accept the homework, you will play with these parameters. As you can see, there are these different regimes. And this is superlubric regime, although it doesn't look like it, but it is. And the area in between is large because we have large velocity. If you decrease the velocity, okay, same parameters, decrease the velocity, and the area shrinks. Okay. While, for example, here, what happened here? So it depends on many things. Okay. Any questions? The code. Let me just show you the code. There's nothing really surprising in this code. So the potential is shown by cosine of x, and the derivative, negative derivative of cosine is sine. So that's why it appears as a force here as a sine. Do you see? That's the sine. Then you have this gamma v plus RT from previous chapter, right? divided by mass of the ball. This is the spring constant, and that's the acceleration. This is the distance. X equals vt plus 1/2 at squared, and v is updated like that. The rest is plotting. Okay? And how do I plot the potential? The total potential, I mean this white part. Okay? That's cosine plus the spring potential. Okay? Very simple code, very simple concept, but this one explains why we have friction independent of velocity, mostly. Let me show you how that is seen over here. So, for example, here you are in superlubric regime, and the friction force goes to 0 as the velocity goes to 0. Do you see that?
Yeah.
But if you are in stick-slip regime, which is k is less than 1, then as you decrease the velocity, you don't go to 0. And in general, if you are doing an experiment and if you are a bit sloppy, you might think that it has actually no dependence on velocity, because most of it comes from friction that you already have when you have almost 0 velocity. Does it make sense? Yes?
Yeah.
That's it. This is the chapter, and your homework will be to reproduce one of these plots, I guess. Do you have any questions, comments? Yes?
Can you explain gamma further?
You mean gamma V?
Is it mass related?
Is it mass related? So gamma V is microscopic friction. So that friction is because of, do you remember this large ball interacting with small balls? It's exactly that effect. So it's the dissipation of the system, and once you create non-equilibrium, what do I mean by non-equilibrium? Once you create motion, for example, in a certain direction, motion in a certain direction is non-equilibrium already, because equilibrium thermodynamics requires you to have velocities in all directions, random, everything random. So you stop, this stops moving, that's already non-equilibrium, okay? And if it's in a superlubric regime, the non-equilibrium is as much as the dissipation is. So it's just, you create non-equilibrium just in the right amount of the way it dissipates. But if you are in stick-slip regime, you are creating extra non-equilibrium, because not only you are moving the system like this, but also you are creating this stuck stuff that then move very, very suddenly. So you create even more non-equilibrium, and still you can't get that back. It does, like, just because you created more non-equilibrium doesn't mean that you are going to get a little bit of it back. That's the thing with this dissipation. It's like a friend that never gives you back what you borrowed, what you lent. Okay? I mean, no matter what you put in the system, it will dissipate. You will not gain back that as mechanical energy. So, does it make sense? So gamma V. Gamma V is this natural dissipation stuff that is inherent to the system, to its microscopic interactions. But when you are in stick-slip regime, you are creating even further non-equilibrium. When you are in superlubric regime, you have just enough friction, same amount of friction as inherently present in the system. Does it make sense?
By the way, can I ask a question?
Sure.
In encounter in daily life, in entering, etc., how common are super lubric regimes?
Very good question. Not so common. Not so common because you need a very smooth surface. Okay.
And we tested that stick slip regime on, when we tested stick slip regime on when we tested stick slip regime, we had very small variations in force, something like that was initial value, and that was almost like that.
Mm-hmm.
But what about what we get in, say, the amounts of force that we get in daily life? So very big with spectrometric scales.
Mm-hmm.
Then how do they in the amounts of sorry.
I actually get your question. So your question is this. To get into the stick slip regime, we needed a huge pressure, right? But that huge pressure is already present in normal situations because of what I mentioned at the beginning of the lecture. It's because of apparent contact area and real contact area. Okay? We might be thinking that this 1 kilo object block is sitting on the 1 meter squared. No, that's too much. 1 centimeter squared, that's too little. 100 centimeters squared area, right? But it is not. What it is touching, the real contact, is much smaller, okay? Since the real contact is much smaller, the pressure is much higher, okay, on those contacts. So once we put a block, we don't see it. There are these YouTube videos where they go like this on the thing, like you cut something and then they close up, very, very microscopic. So if you put the block and zoom in, you will see that the block is almost not touching the surface. It's just protrusions that just interlock. So once you start moving that block, those protrusions do this ding, 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 and create all those non-equilibrium, and that's dissipated because it's a friend that doesn't give you back what you borrowed, or no, what you lent. Okay? Are we happy? Can we stop here? 1 chapter done. It doesn't mean that its homework will arrive soon. You will still have another week after this homework to do this homework. What you have right now, homework 5, is the simplest homework that there will be, so please don't miss it. That's 1. This homework is much harder. So let me just announce it and you start working on this one. Okay? Good luck. Bye-bye.